Denovit from University of Tennessee, Knoxville for a little over a year now. We're about 60%, 70% of the way through, but it's on stability of reinforced concrete columns. Okay, so kind of as an overview, it's to develop guidelines for the efficient design and assessment of RC bridge columns. So in comparing approximate methods like from AASHTO, moment magnification, as well as refined second order analysis methods. And the basis for this was that the Caltrans wanted to look a little more closely at some of the AASHTO methodology, which is largely based on building codes, not really bridges per se. So to see if some of those analogies carry over, and then look at how the conservative assumptions that are made by bridge engineers, how those could be assessed, or if there's some knowledge gaps to be filled there. Okay, so in this project, we'll evaluate the AASHTO approximate method and the refined method using second order analysis using OpenSees, and then identify some of the controlling parameters like slenderness ratio, LOPD, superstructure stiffness, reinforcement, other parameters. Okay, and then look at or find cases where approximate and refined methods deviate, predicting column strength. Oops, wrong way. Okay, so we'll use a lot of off-the-shelf OpenSees components for short-term loading with single columns, and then compare with an experimental database, which I'll talk about at the end, and then also extend to long-term loading behavior using some recently developed models in OpenSees for time-dependent concrete behavior, which incorporates shrinkage and creep. Okay, and then develop OpenSees models for bridges. So look at single columns, then go to system type behavior, and then you extend the bridge models to also include long-term behavior. Okay. Okay, so a lot of words on this slide, but we're try to Mark and I both like Python and automation, and we're going to develop a procedure, or we have developed a procedure to determine the maximum permitted applied loads according to the design methodology. Compare that to OpenSees models, and then kind of just run parametric studies to evaluate selected cases and analyze data to quantify accuracy and find any shortcomings. Again, because the AASHTO methods are largely based on building type structures and not bridges. Okay, so to start looking at, let me see if I can move this. Well, that's a column over there with a circular cross section. Right? But we're looking at some single column parameter tests, and after talking with Caltrans, including Sharon and Fawad and a couple other bridge engineers, we decided to look at L over D ratios between 5 and 40. Okay, different boundary conditions for this non-sway, this initial non-sway condition. So beta is the ratio of moments applied to the columns at the top. So M at the bottom, beta M at the top. Right, so beta goes from -0.5 for anti-symmetric bending up to 1 for perfectly symmetric bending. Okay. And then different steel longitudinal reinforcing ratios. And then we just kind of locked in 60 KSI, 4 KSI concrete, cover, column diameter, other things with number of selected values equal to 1. Okay, so just initially looking at 128 different cases. So 8 slenderness, 4 boundary conditions on moments, and then 4 different steel reinforcing ratios. Okay, so what we've developed are sets of interaction diagrams. So this is maybe a little hard to see, but the red dashed line is what a traditional section analysis would give you. Okay, and then the other 2 dashed lines, or excuse me, the solid lines are what the AASHTO procedure would tell you is the axial moment strength for section. This is for beta equals 1 and slenderness of 5. Not a very long column, but kind of a short column. But anyway, so the first order moment from AASHTO and from the OpenSees model are the solid orange and blue lines respectively, and then the dashed lines are the second order moments, including P little delta effects predicted by AASHTO and OpenSees respectively. Okay, but you can see from this that as we get to higher axial loads, right, the open seas models give us a higher strength, all right, and indicating the ash toe conservative, if we assume that open seas is right. Claudio showed something about black boxes, dinging bells and stuff. I think he was referring to open seas in a very benign way. But on the right is an error plot, just kind of comparing the ratio or the relative difference between the open seas models and ash toe. Right? And then that angle is, going around the, the eccentricity from 0 to 90 to the error between open seas and the ash toe models. Okay, so do this for all 128 different combinations. Here's another column with beta equals 1, so equal end moments. A little more slender. Slenderness is 10. All right, but again, we see that the section analysis and then the first and second order moments from ash toe, and then the open seas results as well. And again, the open seas results are giving us more strength than we anticipate from ash toe. Okay. And here's a case with beta equals -0.5, so anti-symmetric bending, unequal moments, all right? And things kind of sputter out quite a bit, all right? But this is a very stringent or extreme loading in a way, all right? But here's the section analysis result, okay? And then the ash toe and open seas results for first, second one, okay? But do that over all 128 cases, and we see that the analytical models are mostly conservative, except for cases with low axial load and high moment, where that angle is below 10, 15 degrees. So somewhere on this part of the interaction diagram. Okay. So it's evaluating the methodologies and looking at the individual columns. Okay. Another way of looking at that with different reinforcing ratios, color-coded percent errors. You don't want to stare at numbers, but it's okay. And then also looking at using or developing models with long-term loading. All right, using open seas components coming off the shelf, fiber sections, rotational mesh, displacement-based elements, all that good stuff. But using some of the newly developed time-dependent concrete models within open seas for the concrete fibers, and then just applying an axial load on this column, and then running it out over years of time to look at creep and shrinkage. Okay, so on the upper right is a plot of lateral displacement at midspan, all right, versus time in years. It goes out to 25 years. Okay, but with a concentric load and a slight imperfection, right, we do see that as that load is just held there for 25 years, we do get some creep and shrinkage, increasing in strain, increases in strain, and then increased lateral displacements. And then for an eccentric load, all right, on the bottom right, okay, we get to some, initially some pretty small lateral displacements, but then over time, lateral displacement increases to 0.8 inches or so. Okay, so this indicates that over time, right, the second order effects will become more significant. Okay, so the single columns, how does this translate to bridge models? And this is where we currently are more or less with the project. This is an image that I don't think Sharon took it, but she gave it to us as an example. It's a very nice picture of a fairly slender column bridge somewhere, but looking at column height, column cross section, whether it's circular sections or the double or the, what do you call them, the oblong, the double circle interlocking sections. I forget, they had a oval shaped, for lack of a better term, and then we're going to look at different number of spans, 2, 3, and 4, where the abutments will become less important as you go to more spans. Okay? Looking at single column bends such as the one here, and then multi-column bends where you have frame action, different column conditions, pinned and fixed. Although it looks like maybe we need some SSI on this for this particular bridge, but not the best site conditions, or at least to my untrained eye. But and then simple abutment models. Okay, so after showing you that nice picture of a curved bridge, I'm going to change gears to an ordinary standard bridge, which is straight, all right, no curve. This up. But using a model from a previous Caltrans project, we took was 2-span pre-stressed box girder bridge, and just to get an idea of the assumptions that are made. We increased the L/D ratio for the column in this bent single bent single column from about 3.5, which was the as-built. It was like 18-foot column, 5.5 foot diameter. Up, we just extended it to L/D of 15. We made it slender numerically. Okay. We assigned a effective EI of 0.8, the gross, used roller abutments. We actually, it says no restraint, but we actually restrained the torsion at the ends, which I'll talk about in a second. And we loaded this vertically, not laterally, all right, but vertically with doing a push down analysis. Funny, one of the OpenSeas guys is doing static analysis with vertical loads. Okay. It's lunchtime coming up, but we're basically distributing a load across the deck, right, and then just pushing it down until the column buckles, right, or until the stiffness of the vertical load displacement reaches 60% of the initial stiffness. All right. And then we'll back calculate K factors for the column. Okay, just from Euler's equation, right, which I think we've all seen, right? Pi squared EI over KL squared. You can solve for K, right? So if we know pi, we know L. We know EI effective, right, which was just 80% of the gross, and then whatever the critical axial load is in the column, when we lose 6% of the stiffness, we can back calculate K. Okay, so just doing this type of push down analysis in OpenSeas. For the longitudinal direction, we basically get a K factor of 1. This is an elastic model. We're just kind of doing sanity checks at this point. All right, but it's kind of hard to see, but you get kind of the fixed column and double curvature in the longitudinal direction along the direction of traffic. All right, and that's consistent with the assumptions made by bridge engineers for the stability analysis. Okay, and then the transverse direction, same kind of thing. Right? This thing starts to move transversely, and then buckle also as a fixed column. I guess it's the X direction on this model. Okay, so again, K is equal to 1, more or less in both cases, which is what we would expect. All right, but we're not yet accounting for nonlinear material effects or other things like we did with the interaction diagrams I showed a few minutes ago. But this is kind of getting the initial models developed for system level behavior. Okay, and this came up in our TAC meeting a couple weeks ago or a week ago. But for the transverse direction, right, as the superstructure moves laterally or transversely, all right, are we getting overturning in the of the abutment? Okay, and we basically what we did a little calculation since that last meeting, but basically no, we're not getting any restraint, because if you look at the eccentricity of the vertical reaction at the abutments, it's about 0.4 feet on a 37.5 foot wide superstructure, right? So the statics thing of, you take the torsional reaction, and then, move the force couple over to some equivalent distance. That distance is about 0.4 feet. So that torsional boundary condition is not messing things up unnecessarily. Okay. So I think in the point being that I think in practice, right, for the transverse direction, a lot of times that's assumed to be a flagpole, right, for a single column vent, in which case K is 2. Right. But with an actual restraint, that K factor can come down quite a bit, and with K is lower, you can make your columns column diameters a little smaller. Right? But that's something we're looking into, is these types of system level behaviors. Okay, so that's basically tasks 1 through 4. Right, it's pretty much where we are, and then the future tasks 5 and 6. Develop design guidelines. Okay, looking at effective stiffness, effective length factors, or K, and then design limitations. Then develop final recommendations, and then ensure that those recommendations are compatible with CSI Bridge. All right, it can be efficiently implemented within that software. Okay, and it's not meant to repeat analyses from OpenSeas, but just to make sure that the design procedures can be accommodated within CSI Bridge. Okay, and then an extra thing like a task 7, supplemental task 7, is to kind of build upon the peer column database and start to include a lot of data that Mark Denovitz compiled for steel concrete composite columns, and looking at vertical loading on columns and getting those into to see if all of that can be combined in one database for the SPD, peer structural performance database. Okay, so I think that's it, and yeah, thank you.
We have 10 minutes for Michael or until the lunch arrives. So it is earlier. We want to say anything, Chris?
Closing comment. You said you had more stuff to do after lunch, so you might as well
Great.
do it now. Yeah.
Yes.
Okay. Okay.
About the Delta.
Okay.
I think you have one slide where you might have skipped by it, but it seemed like the Delta and Slender columns is going to be in a fourth bit. Is it part of the study, or is it a separate issue for plans? The Delta effects.
Yeah, it's part of this study.
It's part of the study.
Yeah. Did I?
You do the question first.
Yeah. Oh, so the question was if the P little delta, right, effects, I guess, would be part of this project. And yeah, and I skipped through it too quickly.
But you mentioned you were using a co-rotational.
Yeah.
So.
Yeah, like a mesh of co-rotational elements. So you pick it up kind of automatically.
I just saw one slide where the word.
It might be. I know I have another slide that kind of. Yeah. I didn't show this. This is after the conclusion, but yeah, it's kind of showing that you can get with material and geometric nonlinearity. You're
going to top of the column restrained against swing, but in your results on the two Slender top, you've got without lateral, you've got lateral from the top of the columns.
Yeah. Okay, yeah. On these, yeah, I was putting like a little 1 pound load in the opposite direction just to move things, like scaled up in proportion or along with the vertical load. I had a really small lateral load just to kind of trigger this way or that way buckling. Yeah. But this column here is discretized into multiple elements, so that it'll pick up the P little delta effect.
So the lateral load is the elimination of perfection.
Yeah.